Our first speaker is Samson Johnson, talking about his predictions for the Roman Galactic Bulge time domain survey and the constraints it will provide on the frequency of Earth analogs. So Samson, go ahead.
Hi, thank you, Rachel. My name is Samson Johnson. I'm a grad student finishing up at Ohio State and going to be starting an NPP at JPL come this summer. And today I'm very excited to talk to you about Roman's ability to constrain eta Earth, or the statistic that describes the frequency of Earth analogs. This is work I'm doing with Matthew Penny and Scott Gowdy, and I'd also like to thank everybody else on the the former Roman Galactic Exoplanet Survey Science Investigation team. So to start off, this plot has been showed a number of times. It will be showed countless times into the future, but it's a great place to start. So here, there's planet mass on the vertical axis, and there's orbital separation on the horizontal. The black points are basically planets that we know of or that were discovered from the ground. The red points are Kepler's monumental contribution to exoplanet science. And then the blue points are a potential yield of Roman planets discovered through microlensing. And here, it's going to be at the end of the Roman survey, we're going to have a great characterization of this parameter space. But the ones that I want to focus on today are those in this region here. So your lower mass, modestly separated to widely separated planets that fall in this Earth-like or terrestrial-like or super Earth regime or mini Neptune regime even. And those planets are going to be very useful in determining the frequency of Earth analogs. So this frequency is extremely important because it's a key parameter in designing future direct imaging missions that can detect biosignatures and characterize habitable planets in the coming decades. But right now, our current best estimates are coming from Kepler, and so these Earth analogs were on the edge of Kepler's sensitivity function. So people have necessarily had to extrapolate from shorter period planets and larger radii planets. And here in this plot, you can see sort of the evolution as a function of time of the estimate for this occurrence rate in the habitable zone of sun-like stars. And we can see there's some, it's starting to converge, but any other handle we can get on the statistics is going to be very vital. So when most people think about microlensing, it's usually the picture is, cold Jupiter around an M dwarf. That's not always necessarily the case. And to demonstrate that, here's a cartoon that I made showing here in green this prescription from Kaparapu et al. 2013 for the habitable zone. So obviously, as your host star gets massive, the habitable zone pushes further and further out. Then here is the inner edge, and then the outer edge of that habitable zone. Now for microlensing, the peak sensitivity to planets are those that have projected separations close to the Einstein ring radius of the host star. And so that's a function, it's proportional to the square root of the mass of the host star, but it's also a function of the lens and source distances in the event. And to show that, here are two examples. The first here, the one that sits further out, is for a lens that's around 5 kiloparsecs. And so this one, it gets pretty close to the habitable zone. But if you push that lens closer towards the center of the galaxy to 7.5 kiloparsecs from Earth, the Einstein ring radius actually intersects with the habitable zone for high mass, solar mass lenses. So there is this subset of events that will be sensitive to habitable zone planets for. Now, what would an Earth analog look like to Roman? So here I've got the survey details that have been gone over a few times already. But on the right here is a simulated event that shows a perturbation due to an Earth mass planet. This is the closest I could from random number generation for the simulations to come up with a near Earth analog system. So Earth mass planet around a solar mass star at 1 AU. And here we can see, this few percent deviation coming from the presence of the planet that lasts about 6 hours. So we need to have that cadence, like Scott emphasized, for characterizing these relatively short timescale features. And so if we take a zoom in on these planets here in this region of parameter space, what I did in some previous simulations was to recast those parameters. So on the vertical axis here is planet mass, and then just using the mass radius relationship from Chen and Kipping, 2016, radius is on the other side. And then along the horizontal axis is the semi-major axis scaled by the bolometric luminosity of the host. Here I've coded the detected planets as a function of their host mass. So the large circles are those with more solar type stars, or more solar type hosts, greater than half a solar mass. And then M dwarfs are, more or less M dwarfs are the small diamonds. And here, this gray region is some assumed region for the habitable zone. And as we can see, Roman is going to detect a few planets in this region, but on its own, Roman will have to play the same game as Kepler, or a similar game, and that you'll have to extrapolate the occurrence rate from larger or more widely separated planets and those with higher masses to be able to constrain the frequency within this gray region. And so this was done using the same galactic model as Matthew Penny used in 2019 for those predictions. But right now we are going through and incorporating the new galactic model from Koshimoto et al. From 2021. This model is going to be a large improvement over a number of aspects that I won't get into, but it's going to improve our estimates and hopefully be a more realistic representation of the galaxy. So here in this figure, the previous region searched in Penny et al. Is this small purple box, or the smaller of the two purple boxes. And then their original grid is this black grid that's sort of hard to see. Sorry about that. And then here, the background is the Gonzalez et al. 2012 extinction map. And then the event rate per source is shown as this color, the small circles. And these small circles are new potential fields that we're going to look at using the Koshimoto et al. 2012 galactic model. And so we're going to increase the area, potentially going to, more negative galactic longitudes, and potentially, I'm not totally sure yet, but we might be going up to the northern plane and investigate that as well. But we will be increasing the field resolution so we can really fine tune the placement of the potential Roman footprint fields. And also I plan to investigate cadence more numeric. Like right now we know a bit about it analytically, but from analytic scaling relations, but more numerically go through, actually see if it makes a difference if we were, say, to do a follow-up season of just a single field at like 1 minute cadence, see what that might produce. So right now, looking into fine-tuning these survey parameters, but this is all sort of leading into what I see as like the best prospects for the future for the Roman results, which is combining these microlensing statistics with demographics information from all other detection methods. So with Roman and Kepler combined, just those two data sets, instead of having to extrapolate from either one, we can interpolate between the two and really hone in on this region to refine those the occurrence rate of Earth analogs. But not only that, is we'll have essentially potentially system-wide demographics if we understand those statistics well enough. But there's a lot of caveats in doing that, just because, just in the case of transits and microlensing, transits are sensitive to planet radii and orbital period, whereas microlensing is more sensitive to the mass ratio and projected separation of a planet. These are also potentially coming, or these are coming from different host star populations, which might have an impact on demographic statistics, and also potentially different planet populations. And like I said, as we're sort of to be able to compare, apples to apples, for lack of a better analogy, we need some sort of mass radius relationship, or a way to interpret those different individual sensitivities of these detection methods. So in closing, thank you for your attention. my conclusions are just a quick summary. The quick takeaway points is Roman's going to be sensitive to Earth analog systems. We're starting to work in the new Galactic model to fine-tune survey parameters, and I'm very excited about combined demographics. Yeah, thank you very much.
Excellent. Thank you very much, Samson. And absolutely, that's going to be a very exciting result. So if anybody has any questions, just a reminder to post them in the chat screen of the Zoom session or in the session 4 thread on the Slack channel. And while I have the opportunity, Samson, I know you've done a great deal of simulations of the planet population that will be discovered by Roman. And I've been wondering, have you considered what exomoons might be discovered by Roman? In some cases, they might even be in the habitable zone.
Yes, yeah. So Scott's student, I'm blanking on his last name. Sorry, he's an undergraduate at OSU. They're really starting to dive in on potential detection of exomoons, so triple lens systems essentially. And so we're going to be using these a suite of these simulations to investigate that. But that's sort of ongoing work right now. It's actually a very exciting prospect that I'm excited about, at least.
Absolutely, yeah, fantastic. I'm really glad that's being worked on. And I see that the student's name is Matthew Latovka. Excellent. Look forward to hearing from them at a later date. Are there any other questions that anyone would like to bring up? We have a little bit of time. If not, we will move to our next speaker. Of course, you're very welcome to ask questions at any time during the meeting on the Slack channel. And I encourage all the speakers to keep coming back to this session and follow up on any of the questions that get posed. So thank you, Samson, once again.